Hello, everybody. I am Andrea Keefe, the Meetings and Events Coordinator with IPC. Before we get started, I just wanted to highlight an upcoming event that's currently being displayed. This is the IPC High Reliability Forum and Microvia Summit. This is taking place next month, May 14th through the 16th in Hanover, Maryland. And if you wanted more information or wanted to look at the agenda or speakers, I urge you to go to the website indicated on this screen, or you can email Brooke Sandy at ipc.org directly. I'll also send some information after today's recording. All right, so I'm very excited to kick off today's webinar on weak interface/stacked Microvia reliability concerns. It's important to note that today's webinar is being recorded and will be sent to you via email a few business days concluding this webinar. If you have any questions during today's webinar, please send them using the control panel on the right-hand side of your screen. If we have time at the end of today's webinar, we'll go through those questions and answers. Today, I am pleased to welcome Denny Fritz to be our featured speaker. So Denny, thank you so much for being here. I'll now turn it over to you.
Thank you, Andrea. Can you hear me?
I can hear you.
Okay, let me get my screen share on presentation mode. Andrea, is that clear now?
Yes, looks great.
Okay, fine. Again, this is Denny Fritz. I'm the vice chairman of this working group at IPC. I'm welcoming over maybe as many as 200 registered attendees today, so I think it's a pretty popular topic and very current for IPC. You may know me as Denny Fritz from the 1980s and 90s at McDermott Incorporated, where I worked for 20 years direct and then as a consultant, and also in the last 12 years until last July, I was an employee of SAIC as a subcontractor to the Navy at Crane, Indiana. Just a quick word about the name of this team, IPC V-TSL-MVIA. The TSL in the middle stands for the Technology Solutions Group. This is formed under Mike Carano, who is also on the IPC board. The purpose of this is to tackle big industry problems, and certainly the weak microvias is the first one, but not the only one that we're considering. And the MVIA is the IPC designation of the microvias problem. The purpose of today's meeting is really not to scare you away from microvias. They remain a very reliable construction when properly formed and screened by IPC test methods. I'm reminded of the old McDonald's slogan, millions and billions served. Certainly we make millions and billions of these every day, and they work in general quite well. Today we're tackling a particular issue that's related mostly to stacked microvias. However, it's possible that staggered microvias or even single level microvias, if they're not manufactured carefully into IPC standards, can have field failures. We want to relate our efforts to find the root causes of the phenomenon, and we're working a different path than normal to compile a lot of industry data rather than having to go to very extensive round robin tests. And we want to report what our effort is to date to mitigate this problem. We so far cannot prevent it, but we want to be able to mitigate it. Our overall objective is to make robust printed circuit boards. The section of today's agenda, a little bit on the history of the problem. You can read your copy of the IPC WP 023 white paper. I've got a little bit of the executive summary in here as to what we've diagnosed. You'll see our efforts at creating a fishbone diagram to sort out the causes that could be there and to guide our efforts to compile data and eliminate things that are not factors in it. Data mining is the technology we propose to use on this data we collect. We do know there's reliability modeling and simulation going on, and we'd like to stay in the center of the coordination of that so people don't duplicate it. And finally, we have IPC working teams, and we will be a factor at the seminar in May in Baltimore that Andrea brought up at the start. Just getting going here, a little bit about terminology so we're on the same page with a diagram here. In general, what we're working on are the stacked microvias here in the lower left of the diagram. That is in contrast to staggered microvias that are offset from each other in the upper right of their diagram. It's possible, as I said, to have issues with blind microvias, but with 20 years experience, that doesn't happen very often. And also, you can have buried microvias, and we've not seen an issue with any of those. Anyway, the problem, it tends to be North American oriented. We think that it's because North America is very heavy into aerospace defense, high reliability, where 2 plies of glass are routinely used. So that makes the layer height approximately 75 microns or 3 mils, in contrast to some of the consumer technology of Asia, where the layer thickness is probably on the order of 25 to 50 microns, 1 or 2 mils. Continuing on, we don't think this problem is your routine microvia that we've been making for over 20 years. My own memory of this is that getting going way back in the McDermott days with photolithographic microvias, we thought we had it under control, but our customer came to us and said, you can't just test 10 of these, you got to daisy chain this up into the thousands to be able to test for it. But now we do that routinely, and those are not in general any kind of a problem. In this picture, this is an unetched section from Lockheed. You can't really see much of an interface here. It's unetched. Possibly after the micro etch on a cross section, you can see a weak microface, a weak interface. There's a little differential between the 2 interfaces that are shown in the right picture, but how we really are going to get into the test methods of determining electrically what the occurrence of this defect is. Next, you have a cross section again here from Northrop Grumman. It does show some questionable interface. If they take this to a focused ion beam in a scanning electron microscope, you can see that you have a line, but at 10,000x, it's not much bigger than it shows in the 700x visual that's there. So focused ion beam is the technique that's been used the most in trying to analyze this. Of course, that's $1 million or $2 million a unit, and it's not at all common in printed circuit board fabrication. Much more common in integrated circuit fabrication, but it's not something that we can rely on because it's just not distributed in the printed circuit industry to use as a control tool. Again, as I said, this is almost invisible. These pictures come from Motorola. They believe that this is the interface after reflow that shows up in a cross section. And again, this is very hard to determine. How do you find that you have weak microvias at the interface? The accepted technology today is to monitor the electrical resistance, which is the blue line in this upper left graphic, courtesy of Motorola. They have determined that in the simulated assembly cycling that this interface in the right picture goes open at 224 degrees centigrade, but it doesn't stay broken. It comes back to electrical continuity as the board cools to 184 centigrade. The total here was about 70 seconds of being open, but after that, anything that you did electrically would say that this is a good microvia stack. So this one is one of these interesting problems as an intermittent that when it's broken, it doesn't stay broken. and intermittents are just a horrible problem for us in printed circuit manufacture and assembly. Here's the graphic of the technology that Motorola uses, where they record the temperature in 6 simulated assembly cycles of lead-free. You can see in the left graphic that the weak Microvia stack opened up on the 3rd reflow and remained open on every further reflow. Again, this was their design using stacked Microvias. When they staggered the Microvias and offset them from each other, the board was more compliant and did not show any open Microvias with the same layer count, Microvia layer numbers, et cetera, et cetera. The confounding issues here then are that this problem occurs sporadically. In general, our input so far says you can only find it at high temperature with continuous resistance measurement of your Microvia stacks. It can self-heal as the temperature drops. It's possible that as this self-heals and you have electrical continuity, that the epoxy glass may relax or change over storage. Motorola reports that over months of storage, they've seen things open up again. And the nightmare for everybody in our electronics industry is you get intermittent failures later, most likely after this has been deployed in the field. In going back through the history of the problem, we think that this might date to 2006, but with our information from Motorola, this is again Motorola Solutions in Illinois, they noted in 2010 that they had some kind of an issue, and by 2012 they felt that they had diagnosed this as something that they have brought to us for our inputs and been quite open with their data and their technology. It's been misdiagnosed. I think based on the number of people that are on this call, many of you think that it's an issue that you only have. But one of the reasons IPC is involved is that this is not a uniquely local issue, and it's a common denominator of something going on in our industry that we want to publicize, collect data, and solve this problem. Again, just some other factors here and why it has not come out since 2012. Certainly Microvia layer stacks have become much more common as we need higher interconnection density. It's a low occurrence rate. It's at hot temperatures versus cold. You have difficulty replicating it, so that one of the old adages in our industry is that if you can create it, you can solve it. And we are having trouble replicating it at this point in time. And the traditional acceptance tests of optical inspection or anything that's done at room temperature are unreliable in determining what this is. Directly at IPC, this came to the TAEC group in 2017. Took some months for us to gather enough people that were willing to say they had the problem and contribute to it. The IPC Solutions Exploratory Group started in 2018 and published a white paper last year that I've talked about. Proceeding on then, the current understanding of the problem, and I hope that this gets across to you with either your own experience or stimulates you to being able to contribute to this. Just I can't emphasize enough that it's open at high temperatures and you can find it, but it indicates there's a weak Microvia interface there, and that could fail in the future. So you don't want this in your product. All right, our current activities, right now, all we can say that people are doing and that have shared data with us is they are in the containment mode. They are screening for it. They're trying to prevent any of these weak Microvia boards going out to the field. To do that, they are rejecting some of the product that comes in, and each company has some kind of a screening test, but at this point in time, they're taking a yield loss, and while you'll see Motorola's statistics on this, this yield loss and high cost to use this desirable stacked up Microvia design is causing problems, and we don't want to keep this going and have to inspect quality in. Motorola, for instance, requires a sign-off by a program manager if the design of high layer stacks is to be used in a design. The test method that Motorola has used is under IPC test method 2.6.27a. It's a multiple reflow with continuous resistance monitoring. There are certainly other test methods under the test method committee under 2.6.26 that may be used. I think that we are soliciting experience in using these other test methods for their pertinence in preventing or certainly screening out weak microvias. So again, we're in an industry scramble over the test methodology to be used. The white paper, WP023 from the Weak Microvias Committee, it does outline that there is a weak micro interface somewhere between the target pads and the electrolytic copper. There's the potential here of electroless copper being involved. We're looking for more data on direct metallization and what the effect of that is, and we would solicit inputs from any of those. Again, I can't emphasize enough that if you electrically test at ambient temperature, most likely you are not going to find this problem. Continuing on with the white paper executive summary, our effort really is to try to sort this out and limit the number of experimental designs and stuff that have to be done. And really we're into an effort to try to use data in the 2019 mode and sort that rather than have to run thousands of printed circuit boards with different variables and different locations, et cetera, et cetera. So anyway, we want to understand the deficiencies, establish appropriate test and inspection protocols, and make sure the resources are in the field to analyze the product. To sort out the variables, we at the committee are using a technique called a fishbone diagram. Before we get to the factors, most people think, well, making microvias is a pretty simple process. You just have two layers of conductivity. You create a hole in the upper layer, either you drill it or etch it out, and then you remove the glass epoxies there. You clean the landing pad. You deposit some conductivity across the sidewalls of your microvia, and then you plate it full. And acid copper plating is the one that does that. So we do have one interesting committee member that is mechanically microvia drilling at this time, so it will make an interesting comparison between the generally accepted process that I show you here and the process that they use. The fishbone that we've come up with looks like this. It's kind of the 7M approach. The machines that are used, the methodology that's being used, materials that are involved, any inputs that come in from your instruction or supervision, the measuring tools that you're using to determine the problem, and are you maintaining your operation such that at the start of the time, everything was okay, but you're letting your process drift. And then I guess Mother Nature would be the stuff happens thing where we can't determine really that there's a cause and effect, but anything that we can't put in these would go into the Mother Nature category. Based on these many inputs, we're trying to do a data mining exercise, and we solicit your help in going through this. Our hope is that we don't have to start at ground zero with this round robin testing. There's a limited amount of that going on, and it may evolve to that. I mean, Mike Carano has told us that he would take to the IPC board a request for funding for round robin testing if that's what it gets to. Just a quick understanding of data mining, and these slides come from Happy Holden. It's the extraction and so forth of the knowledge that's there. But to do this, we need a database. And I would say that right now we're have completed about 3 of the items under the process, and we're into the potential of bringing in models, evaluation, and then of course we'll submit our conclusions out to you. To gather data in January before the IPC Expo, we drew up an extensive checklist from the Fishbone diagram. And don't be scared off by this, because we do get a number of these back, but there's a couple of things that we want to really emphasize with you before you submit data. The first one is that IPC will randomize this data. I don't know what Chris Jorgensen down here will do with it, but he's our clearinghouse as the staff liaison to give it your data, a letter, a number, or something like that, so that it's blind to the rest of the Microvia team as to the data that you're submitting. And the next one that's at the top of the chart includes a quick checkbox, so that we would like to know at least what has been tested, that you have field test data from something that you've done. If you will not be willing to share it, you could check off, or if you're willing to share it, that's a second check mark, so that we get an idea of the testing that's going on and whether we can share it. Or possibly if you have a test that's underway right now, and we'll solicit your comments. But I can't emphasize enough that we can't data mine unless we get this data back and develop an understanding. Happy says that the next steps in data mining are as follows. This is beyond me, but I think that Happy will be giving talks at various times, and certainly our committee will be working through this. This is an example of one that Happy did in working with an Asian manufacturer. So far, we've not done a formal failure mode effect analysis, but focused on the weak Microvia interface. And the problem is that it's allowed to escape out to the field. This is just an example of a numerical scoring that Happy did in his past data mining efforts. So rest assured that we've got an industry expert in data mine along on our committee. Reliability activities that are going on, I only can enumerate a couple of examples, but a number of other people, I've got 2 examples here, and I know of at least 2 more activities that are going on in terms of trying to model things. NAVC Crane, the executive agent for printed circuit boards, is working with these parameters and has internally funded a data modeling approach to try to determine some of these parameters and so forth, and contribute that to the efforts of the weak Microvia's team. Another example is this one from CALS. This comes from a PhD thesis. Again, they are simulating up to 4 levels of Microvias, different aspect ratios of the Microvias, and what the stress levels could be. Pardon me. So we know that they are one of the people that has published some data modeling result. Currently, Motorola Solutions has volunteered this mitigation plan, and as I go through it, you'll see what their success is in containing the issue, but they are very active in trying to understand it and try to prevent it with the things that you'll become obvious in what they use. Okay, the historical quality control methodologies for circuit boards, both at the circuit board level itself and at the product level where the entire assembly is tested. Microvia reliability, of course, is hard to analyze based on the structure. And then these are measured before and after the stimulus, but not necessarily continuously monitored as the stimulus is being applied. And then finally, burn-in has monitoring, but its temperature is not nearly as high as the simulated reflow temperatures that we're seeing that indicate the presence of a weak interface. Motorola has enumerated these, and I had shown you previously that they use 6 cycles. They use a 4-wire resistance measurement with theirs. They do use features that are common to that circuit board itself, so we're not testing something that's out of the ordinary. They reject any panel that shows an open or an interconnect issue on any one of the boards on that panel. They've chosen to use the test methodology that I enumerated, but it's possible that others out there have other accepted, IPC accepted test methodologies that could be used. You just have to demonstrate those and work between the board fabricator and the board assembler. Motorola's own experience in yield has gone up over the last 4 years. They're up to 94% now, but they do still reject some product. And likewise, their analysis says that, at least historically, they have more problems with 4-layer stacks than the 3, and the 3 more problems than 2, et cetera, et cetera. However, with their test protocol, they feel they've had 0 product failure since they put this into practice. I think I hit the backward. There we go. This is Motorola's design approach. If you can make it with staggered microvias, make it that way. If you've got a 2-level stack, that's okay, but if you have to go to 3, you have to offset at least 1 level. And if you need 4 levels, you have to offset twice. Trying to minimize any stacks that are greater than 2. And again, as I said, if you got to be above 3, you have to have a program manager sign off for that design and be willing to understand that he's taking a chance with weak microvias. In determining how to tackle the problem, we've divided things up pretty much based on the Fishbone, and we have 7 sub-teams. The first one relates to design, simulation, and modeling. This may be a little bit out of date, but they're working on their scope, and Joe Barber from Raytheon's a team leader. The characterization and test methods, again, this is, I'm sorry, on laminate materials, this is determine the stress from laminate. Doug Jeffrey of Electrotech is the team leader. The construction and design elements, Steve Murray of Northrop, and Happy Holden, who is retired but very active in our group, are co-leaders on that. The metallurgy and the chemical processes team so far have been meeting together because the chemical processes create the metallurgy. I don't know whether these teams will merge or not. Norm Armendariz from Raytheon is leading that group. A hole formation, this again is how do you get either laser, or we have one example of mechanically drilled microvias. Mike Jennings is with ESI, and Jimmy Bockham is with Lockheed. They are co-chairing that working group. And data collection, I think you would gather from my comments that Happy Holden is the fellow that's in charge of all of this. So in summary, we are, as a committee, have told the world that stacked microvias can fracture at the interfaces. The worst would be if this opens up in the service life out in the field. I think you understand that it's unpredictable and you have to test for it. Current industry methods have not been terribly effective. We continue to work. One of these is the 27A, but we are looking for inputs from other cycle manufacturers, equipment people, et cetera, on some of the 2.6.26 test methods and how they have been used to reliably detect this problem. Design can be used to the extent that you run out of space and you have to use stacked microvias. There may be more than one root cause, and we're certainly in containment mode, and we're working to try to identify all the issues and solve this, hopefully by using mostly data rather than enormous round robin testing. Where can you help us? Again, this is the Microvia Reliability Summit in Baltimore. We, as a Microvia's working group, have a session on Monday afternoon from 1 to 5. It may break into the sub-teams. This agenda is not completely set, but we've reserved the room, and we have conference call capabilities so that people who want to dial in can listen in. And then I have a little plug here for the IPC SummerCon. This is the meeting, standards meeting that's been moved from co-locating with the SMTAI meeting in October to June in Raleigh, North Carolina. We will be having Week Microvia's committee meetings at this event. Finally, please help the Week Microvia's team. The long-term goal is high reliability and robust printed circuit board structures. Again, contribute data that you have through Chris Jorgensen and join one of the working teams. Thank you very much today, and I think that I am open for questions at this point in time. So Alicia, how do you want to do this? You want to go back to a lead slide, or you want to drive the questions and I'll answer as best I can?
Yeah, I will drive the question, so we'll just leave the screen blank for now. So as you said, we'll now take questions. We have actually received quite a few, so I'll go through those. And then I just want to note that we will be providing the presentation in PDF form and a copy of the recording within the post-webinar email. And then I will be also including Denny's email address should you have any questions directly about this webinar. And then I'll also be providing Chris Jorgensen's contact information should you have any questions about the committee and such. All right, so the first question I have for you is Motorola doing all 6 incoming tests at once or sequential?
I can't completely answer because I've not been to Motorola and watched their testing. I believe that they certainly run the reflow simulation test completely on everything. They have published a paper, which I think we have access to distribute from the introductions, for instance, at the IPC Expo meeting back in January in San Diego. So I would probably have to refer some of this back to Jerry Majera of Motorola, who's been a key team member. J.R. Strickland also is of Motorola and has helped us a lot. Thanks.
All right, thank you. Another question, what is the best way to monitor progress of the testing / analysis?
I think this is, to me, on 2 levels. One is to follow the progress of the test methods activity within IPC as we drive to get acceptable test methods that can be run with relatively common equipment, are not prohibitively expensive. You heard my comment about not requiring a focused ion beam unit at $1 million to $2 million just to look for weak microvias. On the other level, it would be, my suggestion would be to join at least one of our working groups, hopefully on the test methodology subcommittee, and participate with us in the answers that our team comes up with.
All right, so the next one is using the D coupon as a test method effective?
I think that there's industry controversy about this. It's something of a loaded question. The committee has had the most data submitted about using the D coupon. However, there's other opinions out there that other methodologies will work effectively. What our committee needs is the data behind those beliefs, and that is lacking at the present time. Let's hope that some of that data comes out either at the Baltimore meeting or at the Raleigh meeting in June. I know that some of this activity is starting to spill over into product requirements and activities in the acceptance of circuit boards. And we'll do what we can, concentrate on the weak microvias, but I don't think we're going to demand something as a working committee over on the board acceptance side.
Okay, so next one, can you share the actual WP-023 or do we need to purchase it?
Andrea, they've thrown you in as IPC staff. My belief is that you currently have to purchase it. However, I leave that to IPC staff to give that one out by itself. I mean, I have copies from my work on it and things like that, and you know, it's easy for me to refer to it, but I believe you have to purchase that.
If they join the committee, do they get one for free?
Boy, now you're throwing me in to make policy. I would think through Chris Jorgensen that if you're an active committee member, we'll take care of you. And Chris Jorgensen may slap my fingers afterwards or something like that. But in general, IPC's policy is to give good working people the tools that they need. And IPC for the people on the committees has been pretty free and papers, standards, things like that. You know, if you're along for the ride, I'm not going to encourage Chris to accommodate you.
I would support that. Okay, next one. Has anyone indicated that there is a minimum diameter in regards to mitigating against the issue, i.e. surface area for connection to underlining pad?
Good questions. Good questions. I think that you could see in some of the modeling effort, we know that we've got some of the issues under test. Does the size of the microvia matter? Does the amount of contact between the electroplated copper and the capture pad, or I'm sorry, the target pad, does that affect the reliability? There may be data already submitted to committee, but we certainly are looking for that kind of data to determine that. You did see a little bit of modeling of the aspect ratio of the microvia, and that could help determine the stresses that come from the epoxy glass or unreinforced films or whatever you're using for your dielectric. But a good question. I can't quote it personally myself right here. Others on the committee may know an answer, and I think we're looking for more data.
Thanks, Denny. Another one, I did not see any mention of IST testing as a way to identify weak microvia interfaces. Do you use that? Do you use this method?
The problem that we have as a committee right now is that our sources that have contributed have given us the most data from alternate test methods. I think that some of this may easily be explained at the May meeting. I know we've got a paper from one of the other companies that has a thermal cycling device. I have understood that there's extensive data on IST testing, and IST is the most common piece of thermal cycling equipment that's out there. However, just sitting here saying that we have the data in hand, please submit it if you've got this data. It would make it more fair for everybody on the committee if we do get good, credible data that that methodology prevents shipment of weak microvia boards.
Okay, so this is just a statement. We can send you our cross section we received from someone.
I think, go ahead.
Go ahead.
We would take that. I think that in filling out the form, there's a place in there for data or pictures or something like that, and that might be all you do. And Chris would be happy to sanitize that so that those then pictures could be shared with the rest of the committee. I think that'd be great.
All right. Next question, what possible root causes have been identified? There has been plenty of time to determine some possibilities.
I think that personally, having been in this industry for like 40 years, I don't think there's a single cause. I mean, this one smells to me like there are multiple causes possible to do this. I think that the oldest accepted cause of weak microvias was improper cleaning. And just after you've drilled it, what do you have left? Do you plasma clean it? Do you chemically clean it? How much of the a target pad do you rough up in terms of a micro etch? How do you leave that? And there's not generally industry standards for that. The more insidious problem that's here is there something about the electroless copper or something about the direct metallization that leaves something behind? If you're old like me and you go back 25 or 30 years, you're involved with post-separation issues inside the holes on a multi-layer board. And many of the aspects of this remind me of things that happened back there. At the start, I think there were people that wanted to call it type 1, type 2, type 3 failures, just as had been designated for post-separation on multi-layer boards. That's a much more insidious problem that we're looking for the data and the testing that people have done. So again, I'm concerned that there may be enough causes that we are limited to mitigation rather than prevention. But certainly some of our data will tell you better practices to use as we develop our models and come to conclusions.
Thanks, Denny. All right, we have about 7 more questions, so I'm just going to go through those. You mentioned that 2-stack is preferred max. What dielectric thickness and copper thickness combined is this based on, or what is the maximum microvia barrel height that is reliable?
I can only quote what Motorola has given us, and Motorola is a supplier to the high reliability aerospace, defense, communications, et cetera, et cetera. And my belief is that they are principally using 2 layers of dielectric for that construction. So that would minimize it out at somewhere around 3 microns total, or 75 microns. In terms of copper thicknesses, I don't believe we've got a lot of data. You just would not want your target pad to be etched through, or whatever via formation methodology you're using, it should not etch all the way through that. Is there a visual topography that would be appropriate? I know one of the people that has shared data has given a number of different visuals of what that copper looks like after drill, after micro etch, types of foil that it's used. But in terms of giving absolute numbers, Motorola limits their design to 2 stacks. Okay, I would say that that's not a gospel thing. That's Motorola's experience. If you're working with a board supplier that can do 3 or 4 and can show you that his process is robust, I would accept that from them. I don't know that our committee is ever going to say, don't go over 2, don't go over 3, or don't go over 4. Or I know there's some industry data, particularly in consumer, of any layer via that you've got 8 and 12 layers and so forth like that are stacked up. So there's other issues besides the number of layers in the stack.
Thank you. Another one. After a failed Microvia interface has failed and healed, is there any change in the resistance of the connection after multiple cycles from close to open back to close?
Again, I don't know completely the data that's been shared with us, but my belief is that back at room temperature, after being open many times, it can still show continuity and would not be isolated by electrical test. I know that people are working with their focused ion beams to determine if there is a change at the weak interface in terms of the copper properties and things like that. Certainly they're looking for any residuals or anything that could be there at that point in time. Unfortunately, I don't have a complete answer, but my belief is that after healing, this could show electrical continuity at room temperature after many opens.
All right, next one. Is there any recommendation to perform burn in after PCB assembly?
I think that's up to your acceptance for your product. I don't think that we on our committee are going to get into burn-in. I, my only response is way back to solder joints and so forth, that the Engelmeyer models and stuff of solder joints and so forth said, we've chewed up a lot of our useful life by our assembly process. In this case here, the screening is simulated assembly 6 times. So, do you have to do burn-in after that or not? I am certainly not a burn-in expert, and I don't think our committee will get into that.
All right. Has any work been done on flex multi-layers?
I don't recognize any data that's been submitted to us as a committee. We'd love to have that. Certainly, Microvia and Flex is a growing construction that's out there. I think that a piece of that might go, for instance, to our laminates committee that has not been considered yet at this time, because everything on the laminates we've done is epoxy glass or polyimide, something like that. But if you've got any data, please submit it, because we should not ignore that issue.
All right, next one. Were any tests conducted on Microvias filled with electrodeposited copper? If so, what was the result from the test?
I think that all of the Microvias that are tested are in electroplated copper. I think it's generally accepted that this problem has not terribly been observed with insulation filled a paste or something in a Microvia. Likewise, I think on continuity and simplified process to create a Microvia, metalize it in some fashion, and then fill it with electroplated copper is the accepted process of 2019. Certainly there are other processes that have been done and may be one of the answers we're looking for. The Jerry Majera target is he would like to make a copper wire vertically inside the printed circuit board with all the ductility and properties of a regular copper wire. So I think it's a bit of a design related issue, but it's electrodeplated copper in essentially all the Microvias that have been submitted to us.
All right, thanks, Denny. I am going to go through 2 more questions, and then if we didn't get to your question, I apologize. If you don't mind just sending that to Denny and he could answer that via email. We are running over, so I want to be respectful to everybody's time. So 2 more questions here. Once the defect is revealed after reflow or later in the field, who owns it, the designer, fabricator, or assembler?
Wow. You want a nice legal opinion, and I'm not a lawyer. It's kind of hard for me to say. I think, again, to me, it's as agreed between user and supplier and user. If you've taken an order with requirements that you test your fabricated boards to some methodology, I think then the board fabricator owns it. If you as an OEM do not specify enough about the performance that you want, then you got a shared liability, or then it's the OEM's liability. This is going to get very quickly into acceptance testing at the board level, and those activities are already underway, and I understand they're pretty contentious at this point in time.
All right, last question. We are PCB manufacturers willing to share with IPC and see similar defects, but have limited observation means. Where exactly do you think the failure occurs? At which interface? Between electroless copper or reception pad? Within electroless copper? Between electroless copper and electrolytic copper?
This is again, Andrea, this is exactly the determination for post-separation from 25 years ago. I'm not really going to speculate on think. I would say that of those three failure mechanisms, one has been implicated more than the other, but in this case, I think that all three could contribute to this. That's part of my statement, that I don't believe we're ever going to come to one single cause. You know, you might think that it couldn't possibly be between a metallization or an electrolysis and the acid copper, but I think we've got questions in there about hold times between those operations, you know, in the fabricating process. Certainly in post-separation inside of a multi-layer board, there are implications of electrolysis copper, catalyzation, residues that are left from before. Um, that's why we're looking for the data, and we don't propose, if possible, to get again into a round robin of thousands of circuit boards between different locations. My short answer is I don't personally know, and please join the team and listen to the papers in Raleigh and come to the work session. I mean, the reliability in Baltimore and the working meeting in Raleigh.
Thanks, Denny. So like I said, that was the last question we're going to go through. So if anyone else has any questions, I really do urge you to email Denny directly, or if you have questions specific about the committee, Chris Jorgensen is a great resource, and I will provide that contact information in the post-webinar email. Other than that, I think we're all set. And thank you
Andrea,
again.
I'd like to thank about 12 very active members, co-members of this committee, and
Great.
other people on it, and again, solicit your support. Thank you.
Thank you.